Good morning. In this video, we will discuss internal memory, which is chapter 5. So here in internal memory, we are going to discuss the semiconductor main memory subsystems like random access memory, read-only memory, and even in random access memory, we will discuss the dynamic random access memory and static random access memory. And then we will discuss the error control techniques used to enhance memory reliability. So let's see the memory cell operation. So before going to see the memory cell operation, let's see the organization of the internal memory. Like the basic element of a semiconductor memory is the memory cell. That is the very basic element of semiconductor memory. Remember, random access memory, read-only memory comes under the semiconductor memory. Okay, hard disk comes under magnetic coated memory. Okay. Although a variety of electronic technologies are used, semiconductor memory cells share certain properties. So the properties of the semiconductor memory cells are like they exhibit two stable states, which are binary 0 and binary 1. So that is the two states of the semiconductor memory cells. They are capable of being written into that is at least once to set the state. Like read-only memory, you can write only once. In random access memory, you can write anytime. So you can set the state either to 0 or 1. They are capable of being read to sense the state. So you can read the data from the semiconductor memory cells. So this is the diagram. It shows the operation of the memory cell. Most commonly, the cell has three functional terminals capable of carrying electrical signals. Okay, so what type of signals they carry? You see in the diagram. Here you have a select, you have data in and then a control signal. And this is for the read operation onto the memory cell. For write operation. And for read operation, you have the select, control, and the sense. And to say you need to move the data out of the memory cell. The select terminal selects the memory cell for read or write operation. So the select terminal selects the memory cell. The control terminal, here it is, the control terminal indicates whether the operation is going to be a read operation or write operation. So for writing, let's say I'm going to write data onto the memory cell. The terminal provides an electrical signal and that sets the state. So the data will be given to the memory cell and it will be written. The cell will be set to 1 or 0. For reading operation, the terminal is used for output the data out of the memory cell. The details of the internal organization, the function and timing of the memory cell depends on the integrated circuit technology. Okay then. That's not we discussed in this chapter, but I'm telling for an example. So these are the three common electrical signals that are used onto the memory cells for read and write operations. Now let's move on to the types of the semiconductor memory. So there are many different types of semiconductor memory listed in this table. We have random access memory, we have read-only memory, and then programmable read-only memory, and erasable programmable read-only memory, and electrically erasable programmable read-only memory. And the last one is the one we normally use these days, flash memory. So these are the type of the semiconductor memories. and the category. So they come under certain category. For example, our main memory, random access memory comes under read-write memory. That means you can read anytime and you can write anytime to and from the memory. Okay. And for read this one, like read-only memory and programmable read-only memory comes under the category read-only memory. So you can read only. Okay, mean to say the writing process is done during the fabrication process. Like the data is written onto the read-only memory during the manufacturing time. Okay, then the writing process is different for read-only memory, for programmable read-only memory. The writing process is different, but it's written once onto the memory and you can only read it from the memory. And the last three category, erasable programmable read-only memory, electrically erasable programmable read-only memory and flash memory comes under the category read mostly memory. That means you can still write again, but mostly you will be reading from this memory. Okay. So this is the idea of category. And erasure. Erasure means like how are you going to remove the content? Like how are we going to delete the content? That is the erasure mentioned in this uh, third column. So here for random access memory, it's electrically erasable and the erasure is byte level erasure. Okay, you can erase data in byte level. For read-only memory, as I said, the data is written once during the fabrication process. You are not going to erase any content. You can only read from the memory. For erasable programmable read-only memory, ultraviolet rays are used to erase the content and its whole chip level. You can't erase one particular segment. If you are erasing, the whole segment has to be erased. The whole chip will be the content of the whole chip will be deleted. Okay. And again for the electrically erasable programmable read-only memory, it's very similar to the random access memory. Electrically erasable and it's byte level. And for flash memory, it's the same like the previous electrically erasable, but erasure is block level erasure. Okay. So the write mechanism is electrically writing the data onto the memory. And for the read-only memory, it's going to be like the write mechanism is mask, and for the electrically erasable programmable read-only memory and for the flash memory, it's electrically erasable. Okay, you see that this last two category, flash memory and EEPROM, are very close to the random access memory. Even for the erasure, it is electrical, and even for the write mechanism, it is electrical. And the type of the memory, volatile or non-volatile, random access memory is volatile. That means once the power is off, then the data stored onto the random access memory will be deleted. You will lose it. Okay. The data will be lost when there is no power supply. Okay. So random access memory retains the data until there is power supply. Okay. And the rest of the type of the memory are non-volatile memory. So let's move on to random access memory, which is dynamic random access memory. In short, we can call it DRAM. Okay, so this is the dynamic random access memory. The most common memory is the random access memory. So here in random access memory, it's possible to read and write the data to and from the memory. So that is possible. Both reading and writing are accomplished through the electrical signals. This is what in the previous slide I mentioned. Erasure is electrically possible. Even writing is also electrically possible. The one main characteristics of RAM is that it's volatile memory. So it must be provided with a constant power supply. If the power is interrupted, data will be lost. So random access memory is used for a temporary storage. The two traditional forms of random access memory is dynamic RAM and the other one is static RAM. We'll see that in the next slide. First, we'll concentrate on the dynamic RAM. When you talk about the dynamic RAM is made with cells that store data. Here it is. It's made with cells that store data as a charge on the capacitor. As a charge on the capacitor. The presence or absence of the charge the capacitor is interpreted as the binary digit 1 or 0. The presence of the charge is considered as 1. Absence of the charge, the capacitor, is considered as 0. Capacitor have a natural tendency to discharge. So, the dynamic random access memory require periodic refreshing. So, it has to be refreshed in a systematic way, in a periodic way, to maintain the data storage. Otherwise, if there is a discharge, the data will be changed to 0. When there is an absence of charge, then the data 1 will be changed to 0. So, periodic refreshing of the charge is required for dynamic random access memory. The term dynamic refers to the tendency of the stored charge to leak away. So even with power continuously applied, even though the power is continuously applied, there may be a discharge. Okay, so that's the idea. The term dynamic refers, there is a tendency of the stored charge to leak away. Next, we move on to the static RAM, SRAM. We call it SRAM. Static RAM is a digital device that uses the same logic elements used in the processor. In SRAM, binary values are stored using traditional flip-flop logic gate configurations. Okay. In static RAM, the static RAM holds its data as long as power is supplied to it. So just keep it in mind. Of course, random access memory needs power to retain the data, no matter it is a SRAM or a DRAM. So that's the difference between the DRAM and SRAM. In DRAM, the charge onto the capacitor is, the presence of charge is considered as binary bit 1. The absence of charge to the capacitor is considered as binary bit 0. Okay then, but here in the SRAM, binary values are stored using the flip-flop logic gate configuration. Okay, then. So let's see the differences or like the comparison of DRAM and SRAM. So both DRAM and SRAM are volatile. It needs constant power supply. Power must be continuously supplied to the memory cell to retain the bit values. Okay, in dynamic cell, the DRAM, okay, the DRAM is simpler built and it is small. Okay, and it is more dense. Dense means heaviness. It's little heavy because the smaller cells, the cells are really smaller. I told you in the first point, the cells are smaller. So you need more cells per unit area. Okay, and it is less expensive and it needs the like a constant refreshing circuitry because it needs systematic refreshing. Okay, constant refreshing, or else there will be a discharge, the bit value will get changed. They tend to be favored for large memory requirement. If you have a big data, of course, DRAM can capable of storing the big data. So DRAM is used for the main memory. So let's see for the static random access memory. This is faster than the DRAM and is used for the cache memory. Cache memory means do not think it is onto the processor. Some level of cache memory are inside the processor, some level of cache memory are away from the processor. So it is maybe on and off chip. Onto the chip or off the chip. Next we move on to the read-only memory, that is ROM. In short we call it ROM. So ROM, as the name suggests, read-only memory, it contains permanent pattern of data that cannot be changed. The data stored onto the ROM is permanently stored. We cannot alter the data. Okay. So here, as you cannot alter the data, there is no power supply required to maintain the bit value. That means it is not a volatile memory, non-volatile memory. Okay. Data and program is permanently in the memory and never need to be loaded. Okay, so it's there in the memory. So the data is going to stay in the memory forever. Data is actually wired into the chip as part of the fabrication process. During the manufacturing time, the data is stored onto the or written onto the random read-only memory. The disadvantage of read-only memory is there is no room for error. If one bit is wrong, the whole batch of the ROM has to be thrown out. Let's say during the manufacturing process, we write the data onto the chip. In case if there got a wrong data written onto the chip, there is no way to correct the mistakes. Okay, so if there is something wrong in the writing process, the whole batch of the chip has to be discarded, thrown out, because you are not going to manufacture one chip at a time. In a company, you will be manufacturing a batch of chips, maybe like a kind of a million chip or 1,000 chips will be manufacturing in one set. So if there got any mistakes, so the whole batch has to be discarded. The data insertion step includes relatively large fixed cost. Right? Writing process is very expensive. Okay. Next type of the ROM is programmable read-only memory. So as the name it says, here in programmable read-only memory is less expensive and alternative to the ROM. Okay, is less expensive than read-only memory. Okay, then as like a read-only memory, this is also non-volatile memory and may not be written, may be written into it only once. Like during uh, the fabrication process, the data is written onto the memory. Okay, so it is written only once. This is the similarity. Even read-only memory, it's written only once, and that is also non-volatile memory. The previous slide. Okay. Writing process is performed electrically and may be performed by the supplier or even by the customer at a time later than the original chip fabrication. During the chip manufacturing time, we are not going to write it. So the chip will be manufactured and later on it's sent to the supplier or customer. So customer can write the data onto the chip electrically. Okay, so this is the difference between ROM and ROM. And special equipment is required for the writing process because the customer is going to write the data. So there should be a special mechanism needed. It provides flexibility and it's more convenient and it is attractive for high volume production run. The other categories of the read mostly memory. Okay, the three type of memory that comes under the category read mostly memory. So what are the three type of memory comes under read mostly? Electrically programmable read-only memory, electrically erasable programmable read-only memory, and the flash memory. So these are the three other type. Let's look into the erasable programmable. So this one. This is erasable programmable read-only memory. What is this erasable programmable read-only memory? This one, here in the PROM, the read and write is done electrically, as like the programmable read-only memory. However, before a write operation, all the storage cells must be erased to the some initial stage by exposure of the chip under ultraviolet radiation. So let's assume that you are going to write a data onto the ROM. Here the whole chip is going to be exposed to ultraviolet radiation. The whole content is going to be erased. Okay, then so that's the idea of the EPROM. Okay, then so the whole chip is exposed to the ultraviolet radiation. So all the storage cells will be erased, and after that only you will be writing a data. The eraser is performed by shining an intense ultraviolet light through a window that is designed into the memory chip. So this erasure process can be performed repeatedly. So keep it in mind that this erasure takes at least 20 minutes to perform. So thus the EPROM can be altered multiple times. But with the Roman EPROM, it holds the data permanently. But here in EPROM, erasable programmable read-only memory, you can erase the data many times. Okay. Then the next one is electrically erasable. There it is. Electrically erasable programmable read-only memory. This is read mostly memory that can be written into at any time without erasing the prior content. So this is the difference between the EPROM and EEPROM. Okay, you are not going to erase the whole content. You can write into the memory cells at any time without erasing the previous content. The write operation takes considerably longer than the read operation. Okay, the EEPROM combines the advantage of non-volatile memory with the flexibility of being updatable in place. Okay, and this memory is more expensive than EPROM and it is less dense. Okay, remember it is more expensive and less dense. The last category in the read mostly memory is flash memory. This is another form of semiconductor memory, flash memory. Why it has the name flash memory? Okay, flash. See, the name is flash memory because of the speed with which it can be reprogrammed. Flash means it's quick. So reprogramming is very quick. That is the idea. It was introduced in 1980. Flash memory is an intermediate between the EPROM and EEPROM. Flash memory is in between the EPROM and EEPROM here. In between. What does it mean in between? In terms of the cost and in terms of the functionality. I mean to say it's like this one is more expensive than PROM. And this is more expensive than EPROM. So your flash memory comes under this category. Less expensive than EEPROM, more expensive than EPROM, something like that. In terms of performance also, it is in the middle. In terms of the cost and in terms of the functionality. So here the flash memory uses electrical erasing technology. But it doesn't provide the byte level erasure. It's not going to provide byte level erasure. but it provides the block level eraser, not even the chip level. We are not going to erase the whole chip, but we will be erasing the block level. Microchip is organized so that a section of memory cells are erased in a single action called flash. Okay, so that's what it's called, flash memory. Okay, so flash memory supports block level erasure. EEPROM supports byte level erasure. Okay. Next we move on to interleaved memory. Actually, interleaved memory is a collection of DRAM chips, dynamic random access memory chips. It's a group of collection of DRAM chips. These chips are grouped together to form a memory bank. So all the chips are grouped together and it's called a memory bank. Each memory bank is independently able to serve a memory read-write request. Let's assume that we have two memory banks. Each bank contains a collection of DRAM chips. So as we have two memory banks, each one of them can do simultaneously read-write operation. Okay, so if for example, as we have two bank, one bank can do the read operation, at the same time another bank can do the write operation. So read and write can be done simultaneously. Independently we can serve the read-write request. Let's assume if we have K bank, we can serve K request simultaneously. So this means this interleaved memory increases the memory read-write rate by a factor of K. What is K? K is the number of banks we have. If consecutive words of the memory are stored in different bank, the transfer of the block of the memory is speeded up. Okay. So this is about the interleaved memory. Next we move on to error correction. Error correction, which is maybe hard failure or soft error. What is this error correction is? A semiconductor memory system is like subject to the errors. What do you mean by error is? The bits may be changed. Let's say you save a data 1010. Maybe the bits may be changed to 1111. Got some reasons for this change of bits. The data is now different. Before we say 1010, now the data is 1111, which is mistake, error. Can you get the idea? So that is the idea of error. So how are we going to detect the mistake, error, and fix the error? So that's the thing we are going to see now. First, we just see how the bits, why we have the error. Let's see heart failure. When you talk about the heart failure, it is permanent damage, permanent physical defect. Okay, so that is what you call permanent physical defect. That is what you call heart failure. So here, memory cell or memory cells are affected and cannot reliably store data but become stuck at 1 or 0. It's stuck with the 1 or 0. Okay, it can't be, it cannot reliably store data. Okay, then they switch erratically between 1 and 0. Hard error can be caused by the harsh environmental abuse or manufacturing defect or wear. Okay, then so these are the reasons for the heart failure. Okay, soft error. Soft error means it is a random, non-destructive event that alters the content of the memory cell without damaging the memory. Memory is not damaged. Memory is like perfect. But the content of the memory cells are fluctuated. They are altered between 1 and 0. So that's the idea of soft error. This is caused by power supply problem or alpha particle problem. Okay then. So now let's move on to coming error correcting code. The simplest error correcting code is Humming code, which is devised by Richard Humming at the Bell Laboratories. So that Humming error correcting code uses a Venn diagram. You see in this slide, I got Venn diagram. Okay, you already studied what is a Venn diagram in mathematics course. Okay, so this Venn diagram illustrated in this picture, in this slide, they are used to check on 4-bit data word. Okay, so the data word is 4-bit. Example, let's assume that if the number of bits is equal to 4, number of data bits is equal to 4 bits. Okay, then. So let's see how these three circles are representing the bits. Okay, how to represent the bits in this three circle in this Venn diagram. Let's see that. So here you see, let's see the diagram A. Here you have three interconnecting circles. So there are 7 areas, 7 components are here, compartments are here. So this is one compartment, another, and then intersecting compartment, here one, and then another one, another one, another one. So there are 7 compartments are there. So the data will be written in these 7 compartments, and we will be checking the error also in these from these 7 compartments. Let's see how does it. Let's assume that you have a 4-bit data. So let's see the 4-bit data. Okay, let's see your data bit is assume that I have a 4-bit data bit is equivalent to, maybe let's assume 0, 1, 1, 1. This is your data bit. Okay then. So I'm going to check I'm going to record these 4-bit of data in the Venn diagram in the 7 components, and I'm going to find the parity bits, and using those parity bit and the data bit, I'm going to detect presence of error and correct the error. Okay, so let's see the data bits, which is 0, 1, 1, 1. Okay, so let's assume another with this diagram. Let's go with I'll go with this diagram, not my own data. As per the diagram, let's see the data bit is 1110. Okay, I'm going with this diagram A. Okay then. So the data bits are 1110. So this is data bit 1, and this is data bit 2, and this is data bit 3, and this is data bit 4. So you now know what is D1, D2, D3 and D4. So here in the Venn diagram, you need to place those bits. So where D1 comes, where D2 comes, D3 comes, so you need to remember the position. Let me draw it here because I don't want to disturb that diagram. So here in this way, this position is for the D1 and it's going in anti-clockwise. So this is your D2. And on the top is going to be D3, and in the middle this is D3, by the way. In the middle this is going to be your D4. So this is the way we need to position the bits. Okay, I told you there are 7 compartments in this Venn diagram. So we filled the 4 compartments. So we need to fill the 3 more. So we are going to fill the 3 more with the parity bit. So this is parity bit 1. This is parity bit position bit 2. And this is parity bit 3. Okay then. So like this one is going in clockwise means data bit goes in clockwise direction means the parity bit goes in the anti-clockwise, something like that. Okay, you got my point. So as I said, this position is D1, which is a 0, and D2 1. This is D3 and this is D4. Now I need to fill the parity bit. So this is parity bit P1. Here comes the P2 and here comes the P3. Okay, so 3 more compartments I need to fill. How to find the parity bit? So what you need to do, there are 3 circles here, circle A, circle B, circle C. Is it? So you are going to check one by one. Let's consider the circle A. Let's assume I'm following the even parity bit. Okay, even parity bit. So let's see the circle A. You need to maintain even number of ones in the circle. See, in circle A, I have how many ones? 1, 2, 3. 3 ones. 3 is a odd number. I'm using a even parity bit. So you just write 1. Now the number of ones in this circle A is even. That's good. Let's go to circle B. How many ones I have here? I already have 2 ones. It's already even. So P2 is going to be 0. Okay. Go to circle C. How many ones I already have in circle C? 2 ones. It's already even number. So my parity bit 1 is 0. This is the parity bit. How to find the parity bit or how to calculate the parity bit? So for this data bit, this is the parity bits. So this diagram is complete with the data bits and with the parity bit. So let's assume that in this way you have your data and parity. So this is your correct data with the correct parity bits. So in case you save your data in memory and in one point you got hard failure or soft error, maybe some damage to the memory or there is a power fluctuation, and let's assume that your data bit is changed to 0. There is something wrong in the data bit. You see that. How do you, so can you see there is a change in the data? It should be 1 but it's 0. So how computer identifies it? Let's consider the circles one by one and check the parity bit, even parity bit. Let's check the circle A. After filling the parity bit, we maintain the ones as a even ones, even number of ones. Let's see circle A, there is odd number of ones. Okay, let's see the circle B, there is even number of ones. So circle B is okay. Circle A is not okay because we already maintained even number of ones in diagram B. So after some time, if there got a hard failure or soft error, there is a change, is it? So let's see the circle C, only 1. So it's an odd number of ones. So circle A and circle C is having problem. So that means this is the bit which is common to circle A and circle C. So this bit supposed to be not 0. It means it should be 1. So in this bit, this data bit is corrupted. This is the error and you are going to fix the error by making it as 1. So in this way, you can identify where is the error in the data bits and you can fix the error. Okay, so this is the simplest form of error correction code. So this diagram, figure 5.9, it shows the layout of the data bits and the check bits. Before going to see this one, in the previous slide, we saw the Venn diagram, humming error correcting code for single error correction. Even single error detection. We detect one single error and we correct the one single error. In the previous diagram, in the Venn diagram, there were 4 data bits and 3 parity bits. You can call them as check bits. So for 4 data bit, we need 3 parity bit. If it is 8 data bits, we need 4 check bits, 4 parity bits or 4 check bits. Okay, so let's assume that in case if you have 8 data bits. Okay, so now we are going to discuss the data bits which is going to be of 8 bits. So in case if you have 8 data bits, we are going to have 4 check bits. You know, in the previous Venn diagram, we call it parity bit. So here we are going to call it check bits. So for 4 data bits, we are going to have, for 8 data bits, we are going to have 4 check bits. So these are the bit positions. So 4 and 8, 12 bits. So our code is going to have 12 bit. See, the first row says the bit position. So starting from bit number 1 until bit number 2. The next row says the bit position in binary. See, 1 in binary, 2 in binary, 3 means 0011, 4 means 01. So the bit position is written here in binary. This is decimal, this is binary. That's it. So the bit numbers are going to tell you the check bit or data bit. See, bit position 1 is a check bit. Bit position 2 is a check bit 2. C1, C2. The next is D1 and then C4. And D1 is here. So D2, D3, D4 is here. After C4, this is C8. By the way, C1, C2, C4, C8 comes from the bit position. You see, C8 means position 8. C4 means it is bit position 4. Something like that. Remember this. The remaining are given here. So there are 8 bits for the data. And can you see here 4 bits for the parity check bit. 4 check bits. Okay. How do you remember? This bit is for the check bit and this is for the another check bit. This is for another check bit. That is an easy way to remember this. Okay, let's see what is the easy way. So what is 1? How can you say 1 in 2 power is 2 power 0 is 1. What is this? 2 power 1 is 2. Then where is 2 power 2? It's come here. And where is 2 power 3? It comes here. So these are the positions which is check bit. Where you have the 2 power 0, 2 power 1, 2 power 2, 2 power 3. That is the positions for the check bit. The rest of the positions are for the data bits. So just remember this point. So now you know for 8-bit data that's going to be 4 check bit, the position of the data bits and the position of the check bits, the arrangements, the layout. You now have a clear idea. Now let's see, there is a word. Originally you have a 12-bit, 8-bit plus 4-bit check bit. So totally you have a 12-bit data. And you save the 12-bit data correctly. Later on, after a few operations, when you fetch the bit, you get a 12-bit, but it's not going to be same. You are going to check, is it the same or there is an error? And you are going to calculate the check bit calculations and you are going to identify is there any error. You are going to fix the error. Okay. So in this table, figure 5.10, so that type of 12-bit data is stored when it is received, retrieved, fetched from the memory, and it's compared to see is there any error or fixing the error. Okay. I will upload a separate video for this calculation. Deal with the 12-bit code word. Now let's move on to humming code where you have the single error correction, double error deduction. You see that SEC means single error correction. This one is DED, means double error detection. So let's see how does it work. Single error correction and double error detection. Let's assume that this is your data bits. You now know how to fill the data bits in the compartment of the circles in the Venn diagram. So here you need to fill the parity bits. So let's go circle by circle. Let's assume this is circle A and this is, let's say this is circle B and this is your circle C. So in circle A, how many ones you have? 2 ones. So it's already even number. So the parity bit here is 0. In circle B, I have only 1. So I'm going to maintain even number of ones. So the parity bit is going to be 1. And in circle C, how many ones I already have? 2 ones. So the parity bit is going to be 0 because it's already even number. Number of ones is even number. Can you see that? Apart from that, you are going to have additional parity bit which is going to count the total number of ones in the whole Venn diagram and maintain even number of ones. So in my 3 circles, how many ones I have? 1, 2, 3. I'm going to maintain even number of ones with the extra parity bit. So I will keep a 1. Okay. So number of ones in this whole Venn diagram including the extra parity bit is maintained as even number. This is the diagram I just explained in here. Let's assume that there got an error. So due to maybe hard failure or soft error, you see here there got double error here. Okay, so here 1 and this is another one. So there are double error. That means here it is double error deduction. So we are going to deduct double error only. Okay. So there are double error here. Now let's check the parity bits with the data bits. Okay, fine. So this circle A is fine because it's only even number of ones. I don't think so any mistakes. Let's check the circle B. Circle B contains only 1. Normally we don't have a parity with a 1. So what I will do, we will be maintaining a, because here in the circle B, it's 1. Can you get the idea? It's 1. So there is something wrong here. So let's check the circle C. In circle C also there is only 1 here. Okay. So circle A doesn't have any errors according to this positions. Circle B has a certain error and circle C also has an error. So what is the common bit, data bit common to circle B and C? This is the common compartment for circle B and C. Okay. So what we will do, so we will think that circle B has a wrong number of ones. It's not an even number of ones. Even circle C doesn't contain even number of ones. So we assume that the common compartment, common bit here is this data bit. So we will tend to say change it to 1. We assume that is the error bit and we change it to 1. Okay, let's now check. If you change it to 1, did you fix the error? Let's check. Circle A, no errors because it contains even number of ones. Circle B contains even number of ones when you count. Circle C contains even number of ones. Perfect. But the problem here is the extra parity bit. Extra parity bit now contains 1. Let's check the whole number of ones in the whole Venn diagram. 1, 2, 3, 4 with the extra parity 5. There is something wrong. There are going to be double error. So there is a double error. We corrected single error. By the way, we corrected single error. But there are double error. So that's what single error detection, okay, single error correction and double error detection. Okay, we detect the double error. Fine. Now let's move on to the advanced DRAM organization. So in advanced DRAM organization, One of the most critical system bottleneck when using high performance processor is the interface to the main internal memory. High performance processor, the processor is performing in a high speed, but memory normally takes longer time, slow processing. Can you get the idea? So often we end up in bottleneck, the speed problem. Okay, processor performs in high speed, but memory performs in low speed. The traditional DRAM chips is constrained both by its internal architecture and by its interface to the processor memory bus. The number of enhancements to the basic DRAM architecture can be explored. So the scheme that currently dominates the market is SDRAM and DDR DRAM. SDRAM and DDR DRAM. What are the SDRAM? This is a solution for this constraint is SDRAM and DDR. What is this SDRAM? Synchronous dynamic random access memory. This is the most commonly used form of dynamic random access memory. It exchanges the data with the processor synchronized to the external clock signal running at full speed of the processor memory bus without imposing any wait state. So the movement of data between the processor and memory is going to be with the speed of the processor. Okay, so there is no wait state. With synchronous access, the DRAM moves the data in and out under control of the system clock. The processor or the master or other master issues the instructions and address information which is latched by the DRAM. Then DRAM responds after a set of number of clock cycle. Meanwhile, the master can safely do the other task. While DRAM is doing some processing, master will do some other task. So in this way, the speed is maintained. So let's see the synchronous versus asynchronous DRAM. Okay. So synchronous DRAM and asynchronous DRAM. So synchronous DRAM. This is a type of DRAM that uses externally supplied clock signal to coordinate with the operation of its the external pin interface. The asynchronous DRAM is the old type of DRAM. It was used in the older personal computer. The synchronous DRAM is used in the latest personal computer. Memory access. System clock coordinates with the memory access. But here it doesn't use the system clock. Okay, but in synchronous DRAM it uses the system clock. Performance, it provides high performance. Here in the asynchronous, it is of low performance. Manufacture. Manufacture of the synchronous DRAM is high. Now it is relatively rare. Synchronous DRAM is high. Asynchronous DRAM is low. Because nowadays we are using the synchronous DRAM. Asynchronous DRAM is not at all used here. It is rare now. Application. Modern PCs are with the synchronous DRAM. And the older PCs, the traditional PCs are with the low speed memory uses the asynchronous DRAM. Okay. Double data rate, that is DDR SDRAM, synchronous DRAM, but here DDR, double data rate. This is developed by the Solid State Technology Association company. Numerous companies make DDR chips which are widely used in the desktop computers and even in the servers. DDR achieves high data rate in 3 ways. How does it work? How it achieves the high data rate? Transfer rate. High transfer rate. Because first, how does it do? First, the data transfer is synchronized to both rising and falling edge of the clock cycle. Normally, the clock cycle has a rising edge and the falling edge. Rising edge and the falling edge, is it? Normally, the data transfer is done in the rising edge, during this rising edge. But here in the DDR RAM, The data transfer is done synchronized with the rising edge and also with the falling edge. This is the falling edge. Okay, both the rising edge and the falling edge. DDR uses higher clock rate on the bus to increase the transfer rate. And DDR uses the buffering scheme. So because of these techniques, DDR achieves high transfer rates. This was the one I was telling. So in the SDRAM, the rising edge of the clock cycle is only used, but in DDR SRAM, both the rising edge and the falling edge are used. Okay, so not only the rising edge, even the falling edge. Can you see here? Even the falling edge. Okay, so the data is transferred not only synchronized with the rising edge, also with the falling edge. Now the last type of memory is the flash memory. Flash memory is used both for internal memory and for the external memory. It was introduced in 1980. It is an intermediate between the EPROM and EEPROM in terms of the cost and in terms of functionality. It uses electrical erasing technology, and it's possible to erase just the block of the memory, not necessary to erase the entire chip. It gets its name flash memory, flash. Why it is given a name flash memory? It gets the name flash memory because microchip is organized so that section of the memory cells are erased in a single action. Okay, it doesn't support byte level eraser, it supports the block level eraser. It's written here. Uses only one transistor per bit, so it achieves high density of the EPROM. Okay. This is up to the chapter 5. I will upload a separate video for the humming code, error correction and detection, the 4 data bit, 3 parity bit, and also for the 8 data bit, 4 check bits. So check the video for more exercises. Thank you.